Hello, everyone. Good evening. We'll get started now, and I'm sure people will filter in. Um, Hello, thank you so much for joining the California State Library's Information Services and Government Publications section for a very special program of stargazing and galaxy touring with Dr. Thomas Greene and NASA's James Webb Space Telescope. Coincidentally, today, July 20th, marks the 54th anniversary of the lunar landing, so it's a great day to explore space. My name is Mona Robinson, and I'm the host of tonight's event. I'm a reference and outreach librarian in the Information Services section of the California State Library. And tonight we have a co-host, Bradley Seabold, who is a senior librarian in our government publications section. Bradley will be monitoring our Q&A section throughout the talk for any questions you may have for Dr. Greene, and he will read your questions during our Q&A session at the end of the presentation. The California State Library is so thrilled to partner with NASA's Ames Research Center and Dr. Thomas Greene to present tonight's program. The images and scientific findings being generated by the James Webb Space Telescope are truly groundbreaking and awe-inspiring. We're fortunate to learn about the mission and its findings tonight from an astrophysicist so intimately involved with the project. But before we start, we do need to go over just a little bit of housekeeping. If you have any questions during the presentation, please type them into the Q&A section, and we will answer them at the end of the program during our Q&A session. This presentation will be recorded and made available after the demo. If you've registered, you'll automatically get a link. Live transcription is enabled, so if you'd like to see captions, please click the CC icon to show subtitles. If you run into any technical difficulties during the presentation, please put those in the Q&A section, and we will try and help you if we can. Okay, I believe that covers that. Our speaker bio. Now, tonight we are so honored to have Dr. Thomas Greene. He is an astrophysicist in the Space Science and Astrobiology Division at NASA's Ames Research Center. Dr. Greene was co-investigator on the NIRCam and MIRI science instruments of the James Webb Space Telescope and is now using the telescope to study young stars and exoplanets. While at NASA Ames, he has served as the director of Ames Center for Exoplanet Studies, project scientist of the SOFIA mission, and he is the chief of the astrophysics branch. Before joining NASA, he worked at the Lockheed Martin Advanced Technology Center on NASA astrophysics missions. Prior to that, Dr. Greene was on the faculty of the University of Hawaii and was on the staff of the NASA Infrared Telescope facility there. He received his PhD in astronomy from the University of Arizona. So without any further ado, I present to you Dr. Thomas Greene.
Thank you for that wonderful introduction, Ms. Robinson, and thank you everybody that has come out for this webinar. I'm really happy to tell you about the James Webb Space Telescope. It's something that I've been involved in for a while, as Ms. Robinson noted, and it's just fantastic to see it delivering some great science results. So today I'll talk about sort of what we thought it would do and what it is doing, and a little bit about its mission as well. Also, I should say that I put this talk together with the help of many people, and James Webb is a big project, so it really was a team effort. I'll start off by talking about why should we put telescopes in space? It's really hard. And if something breaks, we can't fix it. So it costs like 10 to 50 times as much as a ground-based telescope. Well, three main reasons. So the sky is darker in space. We don't have air glow from the atmosphere. We can see more wavelengths, which is the same as more colors of light. The Earth's atmosphere actually restricts what we can see to a pretty narrow band that matches our eyes pretty well. And also, space is very stable, and there's more nighttime, We don't have to worry about a bright sky here on Earth. If you even if in the daytime, if you look away from the sun, the sky is bright. That's not true in space. And NASA has a long history of putting telescopes in space. In particular, it launched four called Great Observatories. So the first one was this Compton Gamma Ray Observatory, not shown here, in the 90s. The Chandra Space Telescope, it works in X-rays. Then Hubble, which we're all familiar with from its images, works in visible and a little bit of ultraviolet, a little bit of infrared light. And Spitzer was an infrared observatory that lasted almost 20 years. So when I say ultraviolet and infrared, what do I mean? This chart shows the spectrum of electromagnetic radiation. Light is a type of electromagnetic radiation, and our eyes can see this very limited amount of radiation that we perceive as different colors. And just to give you an idea, the bluest blue is to the reddest red is about a factor of 2 in wavelength. So light can be characterized as a wave, and we can measure its wavelength, just like measuring the wavelength of sound, the wavelength of a wave in the ocean, etc. And so the bluest blue light is a little under 400 nanometers, and the reddish red light is about 750 nanometers. So that's pretty short, right? Because a nanometer is 1/1000th of one millionth of a meter. And this shows where the Hubble looked. It looked a little bluer than what we can see and a little redder. Webb is going to look sort of at the red range of what we can see out to pretty far out to about maybe 30 times or 40 times as red as the eye can see. And Spitzer looked even more into the infrared. And there are other wavelengths in the electromagnetic spectrum as well. So what's so great about infrared light? Why is Webb tuned to seeing infrared light? Well, we can see things that we can't see in other ways, is the short answer. Important things. So show you some visible images, visible light of some everyday animals here. So we have some cute meerkats. We've got a freshwater crocodile. That's what they look like in the visible. And in the infrared, though, they're pretty different. So the meerkats are glowing inside in the infrared. You see that they're bright, and that's because they're warm-blooded. They have circulation systems. They're warmer on the inside, and infrared is heat radiation. So it is things that are warm produce infrared radiation. Whereas this crocodile looks really faint, because what I should tell you is that right before this picture is taken, this crocodile was in a freshwater lake that was rather cold, and therefore was not nearly as warm as these meerkats. And it's a reptile, so it doesn't have internal heat generation like mammals do here. Also, with the infrared, we can see through dust. This is a little animation showing that's the visible light of what's called a dark cloud. This is in our galaxy. And so this is like several thousand light years away from where we are now. And in visible light here, we can't see anything. And then in infrared light, we see there's this embedded star, which is blowing a hole in the cloud. This is the side we can see towards us. And that side's the side from away from us. And we see all these young stars that are embedded in the cloud, that are being born there, that we would just not know about if we only had visible light. So you may have seen some of these images. This is showing how we can see through dust and also see the glow of dust with infrared light. This is Hubble took a few versions of this image. They call it the Pillars of Creation. It's a nearby star-forming region discovered by Charles Messier in the 1700s. And you can see in visible light, it's pretty opaque in regions. These are young stars that have formed out of the cloud of dust and gas. And here there's some remnant dust and gas where we can't see through very well. And then in the infrared with Hubble, which sees just sort of a couple times longer than what the eye can see, maybe 2.5, you see there's some bright stars here, like this one, that's just not visible in visible light. And if you go to even longer infrared lights, this was taken with the Spitzer Space Telescope, the stars heat up the dust and it glows, again, because infrared is heat energy. This shows a comparison between Hubble and the James Webb Space Telescope, or JWST. There's just a lot more detail visible, and this is the infrared image of JWST over here on the right. It's actually glowing, and that's what these colors are, is the dust is glowing there. This is a near-infrared image with James Webb, the same one that you saw before. So this is wavelengths between about visible light and out to 5 microns. And again, 5 microns is about 8 times longer than what the eye can see, and 8 times redder. And this shows the mid-infrared, which goes out several times longer than that. And again, we can start to see the dust of the cloud glowing. And we can see the most embedded young stars in both. The stars are faint, you see here in the mid-infrared, because stars are hot. They're and in the mid-infrared is sensitive to cooler radiation. Another thing about infrared light is that it is useful for looking at things in the early universe, because the universe is expanding. Ever since the Big Bang, the whole universe is expanding. It's not just that things are expanding in the universe, but space itself. So if there was a galaxy in the early universe that formed, say, a few 100 million years after the Big Bang, it had stars that would let out visible light. But because of this expansion, we're moving away very quickly, or it's moving away from us, depending on your frame of reference. And that stretches out the light, and it moves the visible light into the infrared. This is just the Doppler shift, the same thing that I hear every day, and I ride my bike to work, and stuck at the train tracks, and Caltrain will go by, and you hear the whistle pitch change as it goes by. So it's the exact same thing, but applied to light instead of sound. It's that the wavelength gets longer, so it gets redder, and we need to look at the infrared to see light from the early universe, where things are moving away from us very quickly. With that background, I can go into the science that Webb is doing. I'll start off with sort of our plan for it. I started working on this first science working group in 1998, and we knew that the most interesting science that it would do would be things we hadn't thought of. And that's turning out to be correct. But we figured that if it were capable in a number of fundamentally important areas, then it would be doing good science. So we had to figure out what was key science questions that likely not be solved until Webb launched, and use those to define its capabilities, its technical capabilities. And we came up with these 4 groups: studying the early universe, like that example of galaxies and redshifted light; studying how galaxies evolve over time; the birth and death of stars, including how where we came from and how our stars got to go out; and also studying planetary systems and the origins of life, both our solar system and other planets as well. So let's start off with this early universe. It's called first light and the epoch of reionization. So what does that mean? So the Big Bang happened about 13.8 billion years ago, and then the universe was very hot, and it took a while for it to cool down enough for atoms to even form. And one of the reasons why it's cooling is because it's expanding, and it has a finite energy, so it's getting colder. And then eventually stars form. And then the stars start to group together and form these first groups of stars, galaxies. Galaxies like our Milky Way, but a lot younger, a lot less massive. So it took a few 100,000 years for that to happen. The rest of the universe is a bunch of hydrogen atoms, and light from the galaxies starts to penetrate the rest of the universe, and it ionizes the hydrogen. It has to do that because otherwise the hydrogen is going to absorb all the light. And after some time, we get a clear universe. So this is called reionization after a few 100 million years, when these sort of light circles overlap between the galaxies. We start to get a clear universe again. So this was something that we wanted to see. We've seen patches of it with Hubble and some other observatories, but we want to go back to this time, this 300 million years, and start to see the first galaxies forming. And how do you find them? Well, you just look in empty space. Look somewhere where there aren't stars. So look outside of the Milky Way, and you will see a whole bunch of things all compressed together. you're taking a two-dimensional picture, but you're sampling 3 dimensions of space, because you can everything along the path, the distance, is going to be imaged. So we could see nearby things. We can see stars in our galaxy, nearby galaxies, out to hopefully these early galaxies. And this is what we saw. So this image was released about a year ago. It's one of the first sort of science proof images, the first release science images of Webb. This is pretty interesting. So this is a cluster of massive galaxies. It was known before, but we're seeing a lot more objects here. So what's interesting about this is that this bright white objects, this is like a foreground group of massive galaxies in a cluster. And I think that's something like 6 billion light years away or something like that. And then way behind there, they're much older ones, and they're getting magnified because the mass of these galaxies actually acts like a lens. It's pretty wild. You see these funny shapes here? And you see the ones that look sort of concentric. That looks like it's concentric with this. These two may well be the same galaxy behind these bright ones. And this is called gravitational lensing, all this wild bending. This is first sort of found with maybe with Hubble, maybe a little bit before Hubble. I remember it being predicted in the 80s. And then also this boosts the background galaxies. So we can see things that are really old, only a few 100 million years after the universe formed. So in addition to taking images, what Webb can do is it can take this light from these objects and divide it up into what's called spectra. And that division is what's shown here. This is with one of the instruments. It's the near-infrared spectrograph. So we can take, this is actually a galaxy in that image I showed you before. I found it just looking through it earlier today. And this is its spectrum, because we can use this other instrument and say, take the light of this little area and spread it around. So it can be spread with a prism. You're probably familiar with that, or diffraction grating, which is something that also spreads light out and could disperse it more highly than a prism does. And then we can identify elements that we have here on Earth that in the spectra. And from that, we can figure out how fast, how far away this galaxy is. So that's what was done here in this image. So this early universe image, these are a number of these galaxies here. These are their pictures of them, and their spectra were taken. And from that, we could figure out how old they were. Like, for example, this one here is the light was emitted 13.1 billion years ago, and the whole universe is only 13.8. So this is about the most distant galaxy that Hubble has ever seen. And we're just seeing this in the first few hours of images with Webb. So once we find the first galaxies, we want to understand how galaxies evolve into present day ones like ours. We thought from the Hubble images that a lot of these early universe galaxies were pretty small and pretty weird, and they are small. And we wanted to study sort of how they interact with each other and then become more massive and get this nice spiral structure like our Milky Way galaxy and a lot of other galaxies in our present universe have. And that takes time. So, and to do that, we have to look at these deep fields, study many of these galaxy shapes, and do simulations of their interactions. This is a set of interacting galaxies. This one's actually pretty close. It's called Stephan's Quintet. You can see it with a large amateur telescope even, although it does not look this good. I'll vouch for that. These two galaxies you see are interacting with each other. They've sort of spiraled in, and this galaxy up here is starting to interact with these two. These are their outer regions, and you see what's happened here is that their outer regions have collided, and and these gaseous arms have been compressed, and new stars are forming, and that's color coded. So the longest wavelengths, the most infrared, are reddest here. And this one is more of a foreground object. It's something like 50 million light years away, and these are a few 100 million light years away. So it's pretty neat. So you can see the interaction, star formation happening, and this is all simulated on computers too to figure out how they evolve over time. One of the things that we have found is that a lot of the galaxies in the early universe that we've seen with Webb are much more structured and ordered and have higher rates of star formation than we first thought. So it looks like stars may be forming earlier in the universe than we first thought. So that is something that is a challenge because the early universe was just made out of hydrogen and helium, and we thought it would take a while to process into heavier elements, and then because we need those heavier elements to cool enough to get the gas together. This shows a collision of this cartwheel galaxy was probably a collision, and we see this ring here of young stars and also this inner ring. So there have been two rings of star formation. In addition to studying the evolution of galaxies, we want to study the birth of stars and planets. So with Hubble pretty much took the first images of disks around young stars. We thought, actually, going back to Immanuel Kant and Laplace, people almost 300 years ago were theorizing about how the solar system formed, and people realized that it probably formed in a disk of gas and dust, conserving their momentum. And we pretty much knew from some measurements that there were disks around young stars before Hubble, but Hubble showed us the first images. And what Webb is doing, it's allowing us to figure out what these disks are made out of, how the matter sort of gathers into planets, how it flows onto the star to build up the mass of the star. This is a beautiful star formation region. This is an image that you've probably seen before of the Greene Nebula. It's in the Milky Way. It's about 10,000 light years away. Here we have bright young stars all up at the top here, and some down here that have formed in this cloud of gas and dust. And they are very hot. They have a lot of radiation, and they are ablating away this cloud. So they're destroying the cloud out of which they formed, and they're also causing it to glow. And that's what these colors are. So they're sort of sculpting a shoreline here. And this is called cosmic cliffs, I think, is by the Space Telescope Science Institute, but I think of it more as a cosmic shoreline, which steals a phrase that a colleague of mine used for another phenomena, but I think it fits. Then in these clouds of dust in which the stars form, we can see what sort of molecules are present. One, to see what sort of just the physics of what's going on there, and what just materials there are, and also materials what planets are made out of, what complex organic materials might be there at the start of the solar system, because we're sort of interested in how life came to be on planets, and we'd like to know what the inventory was at when planets were formed. So this is an image here of a dark cloud. Again, like I showed you a while ago, it's hard to see through here. There's dust being lit up by the stars there, but in the dark cloud, there are these big columns of gas and dust, and on the dust grains, ices form. And here we see water ice here. This is the spectroscopy technique. This is where you take the light, you divide it up. So this is from a few microns out to 5 microns here in their spec. So we have water, carbon dioxide, carbon monoxide, etc. And here we've got water again. So these are just some of the different methane ice at around 3.3 microns. So we can start to see organic molecules in the ices in young stellar systems. And we can see these in disks as well, the disks around the stars that are forming planets. All right. So and speaking of planets, let's go on to planets. I think I have to turn this off, and let me see if I can figure that out. And don't do that. Bunch of options. And yes. So there are over 5,000 planets known around other stars. And the lion's share, so I think close to 4,000 have been discovered by this technique, this transit technique, where you look at a lot of stars, and sometimes you get lucky, and the planet of the star passes in front of the star, and it makes the starlight dimmer. That's what this graph is. So as time goes on, the star gets dim when the planet's in front of it. The planet moves from in front, and the star gets a little brighter. It's not a big effect. It's usually about 1% or less. And it turns out that Webb is using that same technique to study what's in the atmospheres of these planets. And it's even a much smaller effect there. It's pretty difficult to tease out, but it's amazing we can do it. This shows a planet. This is a planet about the mass of Saturn around another star. It's called WASP 39b. WASP is this survey, and this is the 39th system studied. And B means it's the planet of the star WASP 39. This shows with different wavelengths. This is like a red color that the eye can see. There's sodium absorptions, and then we go to longer the eye can see, around 1 micron. There's water, and we go longer still, and we start to see things like this little bump is sulfur dioxide. That was a surprise. We never saw that in a planet before, and we understand now it's made carbon dioxide. This is a new discovery. So Hubble had only looked in this narrow range here and in the infrared. So we only knew about water in planets just because these other molecules don't have these spectral fingerprints or signatures. So we have to go to these longer wavelengths. So now we can see all these carbon molecules, which gives us a much better idea of what's in these planets. And that tells us, gives us a better picture of how they formed. And then we could start to answer questions is, are they like our solar system or not? Do they form in the same way? And speaking of other solar systems, so that was a giant planet like Saturn. And however, we are sensitive to looking at some Earth-sized planets as well with Webb. This is the TRAPPIST-1 system. It's kind of a wild system. It's a very small star. This star is it's like less than 1/10 of the mass of the sun. It's like 0.08 solar masses, and it has 7 Earth-ish sized planets. So these 7 planets are all sort of like the masses and sizes of Mercury, Venus, Earth, and Mars in our solar system, and they receive similar radiation. This planet D and E, they get about as much radiation as Earth. C gets about as much radiation as Venus, and this one gets a little more. But the whole system fits in a tiny space would fit in the tiny space within our solar system, because this star is a lot fainter. So the planets are closer to be about the same temperature as our rocky planets. Again, this shows Earth getting about the same amount of radiation from its star as TRAPPIST-D here. And then C is similar to Venus in terms of how much radiation it gets, and B is warmer. So what we're doing is we're looking in the infrared and trying to look at different wavelength regions to see if we can see any absorptions that belie and tell that there's an atmosphere there. We know on Earth at the mid-infrared, there's a very strong absorption of carbon dioxide. This traps heat. It's heating up the planet, right? We're producing too much carbon dioxide. So Earth has about 400 parts per million carbon dioxide. Venus is much stronger. It's very, you see how broad it is. Venus is almost 100% carbon dioxide. Mars is almost 100% carbon dioxide. Earth is interesting. You see it's got ozone. That's a byproduct of it having oxygen. So, and you would not expect it to have ozone or oxygen if it were truly in chemical equilibrium. So something's driving Earth out of chemical equilibrium, and that is life. So we look at TRAPPIST planets, that solar system with the 7 planets. And so I did the study a little earlier this year. And if it did have a carbon dioxide atmosphere as predicted, it wouldn't seem very hot in the color we looked. It would seem only about as warm as Earth. However, it looks much hotter. It's about 500 degrees Kelvin, which is about 450 Fahrenheit, which is a great temperature for baking pizza, but not so great to live there. So, and that's telling us it doesn't have an atmosphere. So, because if it did, the atmosphere would recirculate heat. Also, the Venus-like planet in the system C doesn't have a substantial atmosphere either. And these results for both of these just came out in June in Nature. So, what's giving us all this great data? Well, I'll talk a little bit about the observatory next. So it's got two sides, and one side, this side is the business end with the telescope, and it's always looking at the coldest space. It's always in the shade, and this sunshade here gives it the shade because, and this other side, the bottom here, is facing towards the Earth and the sun. It's got a solar panel for getting power. It has an antenna for transmitting data. And early on in the mission, this shade deployed, and then the telescope started to cool down. So this side is always cold. If the sun gets on the telescope, game over, mission's over, and it's just going to warp too much. So very different from other telescopes that we have made. It's also very exposed, and it has been hit by a few micrometeorites, which were expected. This shows the size of the Webb mirror compared to the Hubble mirror. A couple things. One, it's a lot bigger. So it's a 6.5 meters or so in diameter compared to 2.4. And it's got about 5 times the area. That really determines how much light it gathers. Also, it's not made out of one piece. It's made out of these segments. These are hexagonal 6-sided segments, and there are 18 of them. This was the previous infrared telescope, which was made out of one piece, but it was a lot smaller. It's less than a meter in diameter. So the extra size gives us both great sensitivity, and it also gives us good spatial resolution, so a good sharpness of the images. And the fact that it's cold gives us really good sensitivity in the infrared, because it has to be cold so that its own heat radiation doesn't swamp the faint infrared signals we're trying to observe from all these things in the universe. This is one of the segments here. So these are about 1.3 meters across. This is the secondary mirror. That's up here in the telescope. So the light comes in, hits the secondary mirror. These are all curved slightly. So the light hits this mirror, and then it goes down this hole to where the instruments are that collect it. This is the tertiary mirror, so that's the next mirror it hits. And this is a fine steering mirror. So we need to be able to keep the telescope pointed very precisely. But the telescope is too floppy to move quickly. So we just move this little mirror to keep the images stabilized. And yes, the mirrors are coated with gold, because gold is more reflective in the infrared as aluminum. And it's about 50 grams. So you're not going to get rich if you go out there, claim the telescope, and melt down the gold. That's less than 2 ounces. This shows some of the mirrors being tested. These are some of the segments being put together. They were actually figured. They're made out of this material. It's pretty wild. It's beryllium. It's only the 4th element in the periodic table. It's very light. And it was mined in Utah, I think pressed in Tennessee into these blanks, figured and polished here at this place, L3 Tinsley in Richmond, and then sent to this Marshall Space Flight Center in Alabama, where they had a cold chamber. And because we had to make them warm and measure them cold, because the Webb Space Telescope, the mirrors cooled off to only about, they're less than 50 Kelvin. So, that's less than 100 degrees above 100 degrees Fahrenheit above absolute zero. So so it was quite a tricky thing to make them warm, test them cold, and then touch them up. So this is not your average telescope. So I thought it might be useful to look at how the Webb telescope compares to a large ground-based telescope. So the biggest telescopes on Earth in the visible and the near infrared are the Keck telescopes in Hawaii. This is germane and relevant for a California audience, because the Keck telescopes are jointly operated by the University of California and Caltech, and NASA has a 1/6 share also. So you see that Keck is bigger. So it's got a 10-meter aperture versus a 6.5-meter aperture of JWST. So it's got about 3 times the light gathering power. This sort of shows just sort of how squat it is, this F number here. So JWST is the telescope's more compact. JWST works over much longer wavelength range. That's because Keck could work at longer wavelengths, but there's just 10,000 times as much background radiation from the warm Earth and the atmosphere than we have in space. 18 mirror segments with Webb and 36 with Keck for each Keck. Now, here's an interesting number. So the mass of each segment, these beryllium segments, only 20 kilograms. With Webb, they are 400 kilograms, and they're already lightweighted with Keck. And the whole telescope, all of Webb, the telescope, the instruments, fuel, spacecraft, is only 6 tons. And that's just because that's all we can kind of get out to where it is, to its orbit at L2. Whereas Keck, just the rotating part, is 270 tons. So the whole thing is more. And because space is a pretty efficient place to operate, it's only about 10 times more expensive per hour if you amortize the cost over the lifetime and all that. But they each have their unique purposes. So we need telescopes both in space and on ground to really unlock the mysteries of the universe. This is a little information on the 4 science instruments. So what's behind the mirror there? So in the near infrared, so from where like a red color where our eye can see out to 5 microns, again, so that's like maybe about 8 times redder than our eye can see. We've got 3 instruments. This near infrared spectrograph, it has many modes. It was showing you the spectra, it was dividing up the light, and where you could see signatures from the constituent atoms in the early galaxies, in the early universe galaxies. Nearest does both imaging and spectra, and NIRCam also does imaging and spectra. NIRCam took most of the cool pictures that you've seen here. And at longer wavelengths, starting at 5 microns going out to 28, we have MIRI, and it takes pictures and it also records spectra as well. So MIRI is pretty versatile. This shows sort of the footprint on the sky, where sort of how big they are. It's not the actual, these aren't laid out correctly relative to each other, but this is a galaxy. It's in the, it's called the Whirlpool Galaxy. I think this is near the Big Dipper. And you could see this again in small telescopes. If you had a dark sky, you could probably see it in good binoculars. And it's a pretty impressive nearby galaxy. And this sort of shows the fields of view that you get with the different instruments on there at any one time. So when we're taking an image with NIRCam, we can't simultaneously take an image with something else, but we can look nearby. Speaking of NIRCam, I thought it'd be worth it's the one instrument I'll give some details on. And that's because this was actually built in Palo Alto by the Lockheed Martin Advanced Technology Center. It was led by the University of Arizona. Marcia Ricci was the principal investigator. And this, again, works from about 600 nanometers of red light for us out to 5 microns. It has 2 pretty identical cameras, and you can see them. They look like sort of a mirror reflection, right? This is this beryllium bench, that really lightweight stuff the mirrors are made out of, and all these gold things enclose the optics and detectors and whatnot. And they have 2 adjacent fields of view on the sky, these 2 cameras, and we wanted to make it very redundant. So that's why they're 2 nearly identical things, because we also use it to align the telescope. We spent about a month aligning the telescope with this camera. And the first time we turned on this camera, we saw 18 images for every star. And then we had to tweak up the telescope. And after a month, we got it aligned for NIRCam. And after 2 months, we got it optimized. This shows sort of like these high-tech near-infrared detector arrays. These are not like CMOS and CCD things like we have in our digital cameras and in our phones. They have different materials that absorb infrared light. Infrared light which is passed through these silicon devices that we have in our cameras and our phones. Some pictures. So this was the telescope being put together in 2016 at a big clean room at the NASA Goddard Space Flight Center. Fortunately, it had a big window. I would go by it when I was testing the instruments and kind of see. Every few days for a while, they'd put another mirror segment on there. So this is the completed primary mirror. Secondary mirror is up near the top. This shows the instruments. This is the near-infrared spectrograph, this thing that looks like a kind of a huge cello case. This is the near-infrared camera. That was the one we saw a couple slides ago. And this is the mid-infrared instrument. And then the other instrument is back there, the near-infrared one, the nearest one, the Canadian one. And so these were all put together in this integrated instrument module. And then that was put into this box, which was bolted onto the back of the telescope. This shows the telescope mated to the spacecraft. So this is at Northrop Grumman. Northrop Grumman in Redondo Beach, so again in California, built the spacecraft, and they also integrated the telescope to the rest of the spacecraft. So here we have the folded telescope. These legs are folded. That's the secondary. So when in space, these pop out. And then here is this big sunshade. It's been described as the size of a tennis court. You see it's got 5 layers of this thin mylar. And that's what keeps the telescope cold and the spacecraft warm on the other side. This is with the sunshade has been folded up and put into these pallets. Pallet structures is what they're called. And the whole observatory is being folded. The yellow stuff is just ground equipment that's being used to handle it. It's pretty tricky to put this together because Webb was made to be really light because the rocket can only lift so much, and it had to be put together in Earth's gravity, and it had to work in 0 gravity. So this is the whole thing folded up, ready to be attached to the rocket. This gray ring there, that's the launch adapter ring where it attaches to the rocket. And let's talk a little bit about the Webb mission from here. So Webb was built by a lot of people. It's kind of interesting. So in late 2021, I was giving these talks. We did a rollout to describe what it would do before launch, and NASA told us, say, about 1,000 people, 1,200 people worked on Webb. These are all the different places where people are. So you see there's a lot of places in California and Europe, because it's a joint project, again, between NASA, about 80%, 20% the European Space Agency, and about 5% Canada. We had some collaborators in Hawaii on the near-infrared camera. So NASA said, oh, say there are about 1,200 people, 1,000, 1,200 people that worked on Webb. And then about a year ago, after it was very successful, we were told to say, oh, 10,000 people worked on Webb. So I think a lot more people decided to say, yeah, we worked on it after it became a success. It was launched here in the Kourou spaceport. This is the European Space Agency's spaceport in French Guiana. And it's pretty close to the equator. It's closer to the equator than Florida, which gives which gives launches a boost because of the rotation of the Earth. And this was just part of Europe's contribution. This was decided early on. It was launched on an Ariane 5. So this here is a rendering of the Ariane 5. This shows a schematic cartoon of how it was folded up into the fairing. So it's a 6.5 meter telescope. The whole fairing is only 5, and you need some clearance around there. So the leaves on the mirror had to fold. So on the 2 sides, sort of like drop leaves on a table. Launched at 4:20 a.m. Pacific on Christmas Day 2021. It was a beautiful launch. This is actually Webb, and you can tell that it really is Webb because if you look up here in the image, you see there's a picture of JWST. And as soon as the launch window wasn't very wide, so you could, I think it was 30 minutes or at most an hour. So it had to launch within that, or else you had to scrub and wait for another day. And as soon as the window opened, the countdown was perfect. It launched. The orbit insertion was really perfect. This is a picture. This is like one of the last photos we saw of Webb. The European Space Agency usually does not have cameras on their upper stages of the Ariane 5s, but they realized Webb is so important, they should put one on. So they did. And what a beautiful picture that is of the Earth's limb. This is the Webb after it left the second stage. This is the adapter ring there. This is the spacecraft part. And then the first thing it did was open its solar array because we had to get sunlight on it. And again, this is just the Earth here, it's just overexposed. So you had to get sunlight on it in order for it to be powered. And then things worked really well since then. There was a sequence of events that took place over about 2 weeks where the sunshade had to come out, and the telescope had to unfold. And we're sort of biting our nails, and you may have heard there are like 340 some potential single points of failure where if something had broken, we'd end up with an imperfect telescope, and it all worked. So that's because we tested things a lot. This shows where Webb is. This is not to scale, okay? Sun's here, Earth's here, and then the moon orbits something like 240,000 miles away from the Earth. And then there's the stable point in the Sun-Earth system called L2. And Webb is orbiting around here. And then so as the Earth goes around the sun, this point follows too. So Webb is always about 1 million miles away from Earth. And it's a nice orbit because if it were orbiting Earth, it would have this nasty day-night thing and would be perturbed by Earth. And here it's very stable thermally. So the telescope can do very stable observations for high sensitivity. And it's also close enough so that we could get a decent data rates of bandwidth from its antenna coming down. So we use the Deep Space Network to bring the data down. Okay, so a lot has happened since that December launch, and it took about 6 months for us to get everything checked out. So about a year ago, it started doing science. So I've showed you some things in its first year of science, and now I'm very happy to show you more. So almost every day, there's another like press announcement. So there are multiple scientific publications every day, and a few of these get picked up by press outlets. And it's like a few a week now that are big enough to be picked up by the press. I'm not going to go over this list in text. It's just sort of here to show you that a lot has happened. Some of this we found just in those little test data when we were commissioning the telescope. We were imaging a bright star to calibrate the wavelengths in one of our spectroscopic modes, this one that I worked on. And in like 10 minutes of data, we found 6 of these galaxies in the early universe in only 10 minutes of data, which just kind of blew our mind, things that Hubble had never seen. So speaking of early universe, this is a big study done by a couple of the instrument teams. So it's about 800 hours done by the NIRCam team and the NIRISS team. It's called JADES, like this JWST Deep Extragalactic Survey. And so this is sort of like that galaxy cluster image where they're taking very deep images, much deeper than that galaxy cluster one, looking for red objects in these deep images. And then what they're doing also is then verifying that these red objects really are things in the early universe. And this is showing some particular objects and their spectra. So they first take the pictures, and then they process them, and then a while later they point again with the near-infrared spectrograph, and they can open up these little windows in the spectrograph to let light in just where these particular objects are. So some of these things are only like 300 million years after the Big Bang. It's a very early universe. This is one of the oldest galaxies. And then they're characterized by redshift. This is a measure of how fast they're moving away from us. And again, you can convert that to age just because the universe is expanding. And much closer to home, we've gotten some amazing pictures of our outer solar system. So this is Uranus. It has these amazing rings here. We can see clouds, weather on it in amazing spatial detail. And then we can see its moons, which not in this picture, but you can see, I think, some of the moons of Neptune here. And you can see clouds on Neptune. So to give you an idea, if you looked at this with a ground-based telescope, you might see 1 or 2 or 3 pixels across here if it wasn't something really fancy with adaptive optics like Keck. And then we can actually see what these clouds are made of in methane, and we can see how the weather is driven. So we want to study kind of what these planets are made out of because these planets are pretty common in the galaxy. These kinds, they're called ice giants. So they're bigger than Earth, and then we also are seeing these rings. So there's this one outer ring of Neptune that The only other time we saw it is when a spacecraft flew by. So the Voyager 2 flew by Neptune in 1989. And now we can study how the ring has evolved. And we're learning from some other observations that these rings could be pretty short-lived. They could be caused by little moonlets being broken up. They can also be used to probe the interior of the planet. So we can get some idea of what the core is like and what the gravity distribution is by looking at ripples in the rings. That's we've learned from Saturn. This is an amazing picture of Jupiter. And no, the colors are not real. The colors are not real in any of these images because we can't see these colors. So what people have usually done is they've mapped the longest wavelengths from the Webb data into the red colors, because red is the longest color we can see. They've mapped the shorter wavelengths into blue colors. Here, they just did a different mapping to bring out lots of contrast. So the person that did this, I think I've got her name on the next slide, is a outreach specialist, science communicator, and was playing around to figure out how we could see all this weather in this in Jupiter's atmosphere. It's the Great Red Spot that we've known about for a while. These glowing patches at the poles are its aurora. So Jupiter has northern and southern lights, just like Earth does, because it has a magnetic field. So what's happening is there's a magnetic field out here, and then charged particles from the sun hit the magnetic field, and then they travel along it and they spiral into Jupiter and hit the atmosphere and cause this glow, this aurora. This is a different stretch, I think, from the same data. And yeah, Judy Schmidt is the person that did the great color mapping here. So this shows a ring of Jupiter. I don't know if you knew that Jupiter had rings. I had to be reminded of it. And some of its smaller moons. And then some of these are like, these spikes are like artifacts, just like when you see a star, you see like these 6 lines coming out of it because of the shape of Webb's mirror. Jupiter is so bright. This is a more recent one. I saw this in May, and I think it came out late May. This is a picture of a small moon on Saturn's moon Enceladus. So this is not a Webb picture. This is from the Cassini mission, which went there. This is a small object. This is, I think, like 300 some miles, like 500 kilometers across. And Cassini found this in this image, like it looked like jets. We're going, wow, that's really wild. So it turns out there's enough tidal interactions between this moon and the planet to deposit some energy under the frozen ice crust of this moon. It's far out, so it's cold. There's an ice crust, but there's a liquid ocean under there. So Enceladus and Europa have liquid oceans. And how do we know it's an ocean? Because of this Webb image. So this is an image here. This shows like hundreds of miles, or thousands of miles away from Enceladus. And we've taken spectra of this with Webb, and this is a water plume. And it's dumping like hundreds of liters per minute. So like 100 gallons per minute of water. And we know it's water from looking at the spectra. We can see the signature of water, of water absorptions. This image came out just last week to celebrate Webb's first year of science. I was very happy about this because I did my PhD dissertation on this cloud. This is the Rho Ophiuchi dark cloud. It is the nearest region of star formation, something like 400 light years away. It's in the Milky Way. And all these stars here that you can see, these fainter ones, they're going to turn into stars like the sun, a little less massive. And this whole group so they've only been forming stars for like 1 million or maybe 2 million years. Most of these stars are younger than that. This is a brighter star, is S1. This is probably a few times the mass of the sun. It has more ultraviolet light. It's lighting up this dust there. And in this dust, there are these complex molecules called polycyclic aromatic hydrocarbons, and they are glowing in the infrared. And that's what we're seeing there. So very nice image of Rho Ophiuchi. You can see some of these, you see like 2 pairs of diffraction spikes here. And that's because there's a double star there. And you can also zoom in. If you go to webbtelescope.org, Webb has 2 B's, they've got all these images there. And you can zoom in and you can see all these little disks from young stars, jets, etc. So lots of active star formation. Here is just very dense gas there, where we can't quite see through the stars. It's so dense we can't even see through in the near infrared with NIRCam. This, I thought, was a pretty cool result. This is an evolved star. So this is a star like the sun's going to be in about 5 billion years. So the sun's about halfway to that point in its evolution. And there's a binary star that orbits around it. And the binary orbits every 8 years, and it's not a circular orbit. It gets closer to the star about every 8 years. And the star that's the bright star here is the old one, has expanded. This is what happens to stars when they get old. The sun, for example, is going to get big, really big. How big is it going to get? Well, it's going to get over 100 times its current radius. So in terms of volume, that's 1,000,000 times the volume. And it's going to come out to pass the Earth's orbit. And that's probably what this star is big like that. And then the atmosphere way out away from the star is no longer strongly bound by gravity to the center of the star. So this other companion comes by every 8 years, and it disturbs the atmosphere, and it causes these concentric rings to be knocked off. This is not an artifact of the image. I mean, it looks like this is real, and they're spaced like every 8 years, and you can measure the expansion by that. So that was not at all known or predicted. So I hope this is give you a taste of what Webb has done in its first year. And again, this is only the beginning. It's taking data almost 24/7. We're already getting some great results. We're going to have a lot more. And hopefully it's going to go on for something like 20 more years. Looks like there's enough fuel for at least 20 more years, if we don't screw things up or nothing bad happens. So please stay tuned. And I'm happy to tell you more later, but I thought I'd just end here about what good is Webb? Why should people be interested in this? Well, you're interested because you're here. But I think it addresses a lot of questions that people have been asking for a long time, since before at least since the beginning of recorded civilizations. What is in the universe? How old is it? How did we get here? Are we alone? And I think those 4 science themes are just more of a scientific way of asking those questions. And I think we're starting to see some results. So we're starting to see some of the first galaxies that formed in the universe. We're learning how they evolved to be ones like our Milky Way. We see how stars and planets form and how the stars die, and sometimes how the planets die too. And we're learning about how planets around other stars are like and unlike ones in our own solar system. And we're starting to study whether any have atmospheres that could support life. Then more concretely, building Webb has advanced our technologies. So people in California, the rest of the US, a lot of other parts of the world helped build it. It's the most complex space telescope ever made. So this is an advance, and will hopefully be capitalized on, advance some scientific astronomy technologies that'll be useful for the ground too. And it's brought thousands of people together, and the science is hopefully bring together a lot more of the world. It's just amazing. It's like I had this little Nature article on one of the TRAPPIST planets. There were over 3,000 articles, over 1,000 media articles about it that had a reach of like 3 billion people. And so people are really interested in these results. And I'd like to thank you for being that. And now I'm happy to take any questions.
Oh, thank you so much, Dr. Greene. That was just fantastic. Thank you so much for sharing your expertise and knowledge with us. It's kind of mind-boggling. So thank you. And we have quite a few questions that have been submitted. So thank you so much for agreeing to stay and take them. And I'm going to turn it over to Bradley Siebel to read the questions to you. And thanks again.
Hi, Dr. Greene. We have a number of intriguing questions. Our first question is, can you see lensing around dark matter?
Well, the technical terms is there's a source and then there's a lens. So the most of the mass that we see in galaxies is indeed dark matter. It turns out that regular matter in our universe is sort of less than 5% or less baryonic matter. And most of the actual matter that we see in galaxies, so something like 70-ish or more percent is dark matter. So when you're seeing these lens images, they're already, even if there's a galaxy with light there, dark matter is contributing strongly to that lensing.
Great, thank you. Next question on your spectroscopy slide of young galaxies from the beginning of the universe. You're seeing oxygen. Are those stars old enough to have that element? Maybe there are a lot of blue giants.
Yeah, so that is sort of amazing. That was one of the things that surprised us, is that there's when you see those elements in emission like that, that usually means there's a lot of star formation going on. So yes, there is oxygen there. Oxygen is a key part of synthesizing hydrogen towards heavier elements. There are a couple different ways to do it. One is two protons together. When you get into these heavier stars, like maybe blue giants, you get into this carbon, nitrogen, oxygen cycle once there are some of those elements, and then it builds up. So yes, and then what we see though is that those in that side, that those elements are normally seen in visible light, but we're seeing them in the infrared because of the very fast expansion of the universe and the large distance between us and those galaxies.
Thank you. Another question, is the James Webb Space Telescope in a fixed orbit? If not, what is the frequency that it relocates to other positions? And also a multi-part, what is the frequency that space dust or particles hit a mirror or any of the sensitive equipment?
Good question. So it is in a fixed orbit. It's orbiting this point, this Sun-Earth L2. I'll go back to that one. And so it's not a stable point though, so it doesn't stay exactly at this point. It here we go. So yeah, move things around so I can see it. So here, so it's orbiting this L2 point. It's got a radius of about 50,000 kilometers. It takes, I think, a month or two to do an orbit. And this kind of follows as the Earth goes around the sun. This follows the Earth here. So that is this fixed orbit. There are a few other astrophysics missions at this L2 point. Occasionally, the orbit is tweaked with the thrusters on the spacecraft. About once a month or so, some small micrometeorite will hit the mirrors. There's been one big one that actually changed the surface quality. We've also changed the operating scheme for the telescope. One of the things we've done is, you see, when it's going around this orbit, we're no longer pointing in the same direction that the spacecraft is traveling. So if it's going this way, it's not going to be looking this way. We'll have it look, over to the side somewhere. And that will hopefully cut down on the rate of these impacts.
Great, thank you. We have another multi-part question. Can you comment on how image colors are rendered? Is this arbitrary or are there rules?
Yes, the answer to that question is yes. So what people usually like to do, they generally follow the scheme of going to, let's see if I can find some of these things here. They find the reddest wavelengths, the reddest colors. So the most infrared are usually given the reddest colors here. Like in this image here, blue is the shortest wavelengths. This is still red for what the eye can see. The stars are hot, so they're mostly blue. And then this is mid-infrared, so it's making it more of a red color. It's just remapping what the telescope sees, because the telescope could see, a factor of 8 or so in wavelength, and the eye can only see a factor of 2. So it's the eye is a much more compressed range of sensitivity. So it's remapping the big range of wavelengths that that the telescope could see into the narrow blue to red that the eye could see, with the blue side, blue, and the more infrared side red. Now, that said, some people will redo the mappings to bring out contrast, and that was the Jupiter image that was done by this outreach specialist, and that it was done just to get as much details as possible without any kind, I think, of color coordination there.
Great, thank you. Can you reflect on a particular moment or discovery that moved you as an individual?
Yeah, so, well, first discovering that it worked was pretty amazing, especially, especially something that you helped build and it actually worked. But something that for me is like I did the study of this first rocky planet, the TRAPPIST system. Hubble had looked at all these rocky planets that are Earth-sized. People have been wondering very intensely. The system was found in 2016. It was explored a little more in 2017. We tried to look at it, every single planet. We've gotten nothing with Hubble and other observatories. And with Webb, I used a different technique. And yeah, I found out, this isn't what the modelers thought. The modelers thought that this planet had an atmosphere, a thick atmosphere like Venus, and there's nothing there. And so that's got some implications for studying life in the galaxy, because it turns out that most planets like Earth, rocky planets the size and the mass of Earth, are not around stars like the sun. Most of the stars that have planets like that are going to be these little dinky M stars, things with less than 1/10 of the mass of the sun. They're going to be like this TRAPPIST system. And so far, we're finding that these planets don't have atmospheres. They may have been destroyed by their stars. So, don't buy real estate around an M star, around one of these small stars, is the lesson I learned there. But it was pretty sobering, realizing that, life may not be as common in the galaxy as we thought. Now, hope isn't lost, because we've only been able to sample the warmer planets in that system. And we haven't really been able to determine whether the cooler Earth temperature ones have atmospheres or not. So stay tuned.
Great, thank you. Another question. Are you currently working on a new telescope and technology that will increase the distance of our universal horizon line?
Well, it turns out that the space telescope that I'm working on that's closest to launch is very different from Webb in a lot of ways, because it's going to be a very small space telescope. It's only 0.5 meter in size. I'm working on it with people at the Goddard Space Flight Center and actually at Lawrence Livermore. It's a very low cost thing. So Webb, with its operations and everything, was like $10 billion, which is a few stadia, right? It's a few things like a baseball stadia, which is a lot of money for science. And this Pandora mission is only $20 million. So, I mean, there's some houses in my neighborhood that are going to cost more than what this mission is. So that's been a lot of fun. And it's going to also answer some important questions in the universe. And we're actually has a little bit of hand-me-down James Webb technology. Some leftover parts are going into it. So that's a fun thing to work on too.
Great, thank you. Another question. Have the discoveries made so far through the Space Telescope affected the estimate of stars that have planetary systems?
The short answer is no, because we're not using it for that. It's like we're using smaller telescopes for the discovery of planets, because you have to look for a long time. And we're using Webb for the detailed follow-up. So what we're doing is we're looking at known planets, and we're trying to get information about more details of their atmospheres, and whether they have atmospheres or not. And that helps us understand maybe how those planets formed, and can figure out whether they formed in a similar way as our own solar system.
Great, thank you. Another question, I know you just spoke about your own telescope work. Are there any plans for a successor to the Webb Space Telescope in the far future?
Yeah, so all the space telescopes have been done, and they've all been a little different. So it's too bad we didn't build 2 or 3 Webbs while we're at it. We didn't realize it would be so good. But the next really big one that's being planned is called the Howdell Worlds Observatory. It's to be about the same size as Webb, and it's going to work more in visible light, and that means it's going to need better image quality than what Webb has. Webb's really optimized for the infrared. It's easier. You don't have to have this precise optical surface as you do in visible light. And so every 10 years, the astronomers get together, decide what they want, and yeah, they came up with this idea. It's also going to look at early universe and transient phenomenon, and also hopefully be able to image Earth-like planets. Now, there's a lot of technology that's going to be required to build this, so it may not actually be operational for over 20 years. So, Webb, like I said, I started with after it had sort of already been thought about a bit, and it took 25 years when I started when science came out. So that's just the price you pay for these big projects.
Great, thank you. Another question. An attendee saw north and east arrows on one of the slides. How do you decide a frame of reference for that?
Yeah, so basically we project the Earth onto the sky. So I had to think about that for a second. It's easier to think about on a ground-based telescope. So the North Pole of Earth points to celestial north. And when you're on the Earth, everything rotates about that. So, you look at, you see Polaris when we're here in the Northern Hemisphere. If you're out like on a summer night, like we have now, you'll spend a few hours, you see some of the stars rotate. Now, when you're off in space, the stars don't rotate, but we have used this coordinate system, we've applied it on Earth, and then we've transferred it to space. But it's pretty much a projection. So when we say something's on the celestial equator, it's projection of the equator of the Earth, and North and South Pole projections of where the poles point.
Great, thank you. Is there any particular galaxy or star that you're personally hoping more resources will be put toward exploring or studying?
Well, yeah, I'm always on these proposals. So the way time is given out is that people from all over the world can send in a proposal about once a year. I think the next ones are going to be due October. And there's about 9,000 hours in a year. They're pretty oversubscribed. So I think the last proposal call is oversubscribed about 7 to 1. So there are about 7 times as much time asked for is what was available. So yeah, I'm interested in a bunch of different planets. Some of the time I did get, we're going to be looking at this TRAPPIST system some more. We're going to be able to better understand the temperature distributions around the orbit to understand the atmospheres of the planets a little more. So that's one of them. And always interested in these different interesting planets, and also young stars as well. I've also have a project in studying protostars, things that will eventually turn in the sun, but they're much younger and they're still accumulating mass.
Thank you. Somebody's interested in knowing if you can share your slide deck to the attendees.
I could do that. I have a Google Drive where I could put it. And then also the artwork, I see the question about the artwork in the background. So maybe it's my Zoom background. And that stems from, there was a public art competition for JWST. So if you Google for JWST public art, you will get that. There's a juried show out of which this image was. This was originally a watercolor with gold leaf. And we're actually talking about that before the webinar. So if you Google for that, you'll be able to see who did it. JWST, public art, and you could try juried show.
Thank you. Another question. I know there have been a lot of findings so far, but and I know you've talked a lot about the notable ones, but is there one that's most notable out of everything that's been studied so far, or?
Well, depends what your interest is, and that's what's most of all. I think the some of the big things that have come out of it are um, galaxies may have formed earlier than we thought. They're certainly forming stars at a higher rate in the early universe than we thought. So things got started with a lot more action in the early universe, and we are the other thing is that there's a lot of chemical constituents in the atmospheres of planets. This thing about these rocky planets not having atmospheres is pretty notable, again, because of its implications for life in the galaxy. Also, I think a big thing has been all of these different prebiotic molecules. They could be precursors for life that are found in regions of star and planet formation. So to me, I think those are a lot of the notable discoveries.
Thank you. Has the James Webb Space Telescope studied molecular cloud Bernard 68?
Funny you asked that. Yeah, I'm a co-investigator on that. I don't know if we've got the paper out yet, but we're that's an interesting cloud. It's a dark cloud. It's where it's a place where I think there is a single protostar forming, and we're studying the molecular components, and we can see through the cloud in the infrared. We see the stars behind it, and we see what complex organic molecules are present. And so we've seen water. I think we've seen methanol, and I forget what other molecules as well, but we are studying that one, yes.
Thank you. Another question. When was the concept of the James Webb Space Telescope first created, and when did construction actually begin?
Yeah, so I'll try to give a short version of that. So by the mid 90s, this is before, I think even before Hubble launched. Hubble launched in 1990, and people realized they needed to have a follow up. I think in the late 80s, people started talking about it. There was this study called HST for Hubble Space Telescope and beyond around 1995 that the older people here like me may remember that Hubble first was flawed when it was launched, and then they corrected it. It's pretty cool. They sent astronauts up to the space with a space shuttle to correct its optics. And then so around 1995, they realized they wanted something that worked out more in the infrared, and they asked for something pretty modest, something that could be a single mirror, something like 4 meters in diameter versus the 6.5 of Webb. But we had a new director of NASA, and he said, no, it will be, he wanted to make it 8 meters, and he wanted to make sure the thing deployed because he wanted to build a bigger telescope in space than other space agencies like the National Reconnaissance Office that does our spy satellites. So he inspired us. So the current version of Webb pretty much started like 1997, like this first concept of it. It got the money and the contracts were let in 2002, launched in 2021. So it was about 25 years from the early studies to science, and about 20 years from when the first contracts went out and said, okay, you guys go forward, and when we got science.
Thank you. Another question. I know the James Webb Space Telescope has sophisticated capabilities. Can any of its functions be used to provide or support for a NASA mission to Mars?
I don't think so, because it's using a lot of off-the-shelf stuff for the communications, and we're taking advantage of the Mars infrastructure more than contributing to it. Like, for example, we're using the Deep Space Network to communicate with it, and those are some of the dishes that are used to communicate with Mars. So I don't think it's going to be, particularly for a manned mission, I don't think we're doing anything particularly useful there.
Thank you. We have a few more questions. This question is, in 20 years, when the telescope runs out of fuel, how will NASA handle that? Is there any way to refuel or repair?
Probably not. So, I showed that Webb has a cold side and a hot side. And the problem is if you really don't want to get anything on the cold side, like, for example, if you sent some sort of robot out there to refuel it, and let's see here if I can find the right slide here. So, if any sort, so a robot would come up, say, fill the tanks, but if any fuel leaked, which it would, because nothing is perfect, it got around here, it would freeze onto the mirror, and then you would cause, then the molecules in the fuel will cause absorptions, and who knows whether the thing could even dock. So I don't want to say impossible, but it was not designed for that. So it'll be pretty impressive if something like that ever gets pulled off. One thing to keep in mind too is that space is a harsh environment. So 20 years is a long time to for things like filters, optics, and for detectors to be there. This is beyond the low Earth orbit, so it doesn't have protection of the Earth's radiation belts like low Earth orbit satellites have. There's some high energy particles coming in all the time. It's like 5 high energy particles per square centimeter per second hitting it, and so it's kind of, and the mirror is going to be hit with more micrometeorites. May not be in very good shape in 20 years.
Thank you. Another question, at the beginning of your presentation, you talked about the technology for the Webb Space Telescope, and they're curious about how you look forward maybe 20, 25 years in the future and decide what will be important for that space telescope in 20, 25 years from now.
What I meant to say is that the science wasn't yet conceived. The technology we got ready pretty early on because we knew that was important. And but you do need to advance technology to advance science most of the time, and that's what we're starting to do now for this follow-up to Webb, for this Habitable Worlds Observatory. We're spending about 10 years working on technologies. So you have to set a science goal out there and then use that to define the technical capabilities, and from there define the technologies.
Thank you. We have a question about the Hubble Space Telescope. What will happen to it now?
Well, that's a good question. So we can't really service it. We lost the space shuttle. That was, and it had to be serviced by people, not robots. People have looked into doing some robotic servicing on it. I'm not sure how viable that is, but the plan is to operate it until it fails. And that should be, we're thinking in the late 2020s. So hopefully it'll have at least 5 more years of life, and it will work simultaneously with Webb, because it's important, because it sees bluer wavelengths than Webb does. So I think it's going to be, and we're actually working on these strategic plans for how to do pair observing between Hubble and Webb. So I think Hubble is going to be really used for things that Webb cannot do.
Great. Thank you. I know we have a question about your sharing of the slides, and I know you said you would provide those to the attendees. So thank you very much. We also have a question about maybe the discovery of life, or how James Webb could potentially detect life on
Yeah.
planets.
So one quick thing about slides: if you go to the site webbtelescope.org, where WEBB spacetelscope.org, and you'll be able to get a lot of these slides. I pilfered a bunch of the images, but I'll also make this set available if I get reminded. If you could please remind me of that, Bradley. Discovered life. So, you know, we've always been surprised. I think we will see things that where life is really the most likely explanation. You know, we're going to see these, like I try to show chemical imbalance that Earth shows. We've got ozone in the spectrum of the Earth's atmosphere. It shouldn't be there. I think we'll see things like that. And then the question is when do we start to see enough of these things so that we get an overwhelming body of evidence such that it has to be life? And it may take more than Webb for that. Also, Webb may find life, and other observatories may find life that's different from our carbon-based life. So I'm hopeful, and we'll see.
Great, thank you very much. Mona, were there any new questions that were submitted?
No, I think you covered that all. And wow, thank you, Bradley, so much. And thank you, Dr. Greene, for taking such a large group of questions. A lot of people have a lot of questions. This is pretty fascinating stuff. So nope, with that, I think I am going to say that it's just about time to wrap up. And I think that we will go to our final slide. And once again, I'm going to thank you, Dr. Greene, for taking your time out. I know I have to tell everybody it was super hard to get Dr. Greene because he's so popular and he's such a kind of a rock star in in the exoplanet world. So thank you so much for being with us. And I just want to tell everybody that we really appreciate you attending, and that the California State Library has a lot of NASA resources. Our government publication section is loaded with them. So if you're ever in town in Sacramento, please stop by 914 Capitol Mall and give us a visit. And so thank you so much, Dr. Greene. And we hope you'll come back and see us again at some point. And thank you all again. Go outside, look up, and enjoy the rest of your evening. Okay, thank you.